Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, good day. Welcome you to the lecture number 18, which is going to focus on analysis for fire, part of the course on maritime structures under fire, blast and explosion, offered in the platform SwayamPrabha by Department of Maritime Engineering at IIT Gandhinagar. Friends, so far we learnt about fire chemistry, fire and explosion as processes. Now we will get into structural fire engineering, where we want to understand how to analyze a system in general for fire loads. So welcome to lecture 18, analysis for fire. Just to recap what we learnt in the previous lectures to understand the consequences and the chemical formulation of fire and explosion processes, we have learnt that combustion of hydrocarbons causes fire. Hydrocarbon is a fuel which is of a compound of carbon and hydrogen predominantly. Methane, for example, will combust to get or to land up in fire. For example, in simple terms, even charcoal burning can also cause fire, which we have been using for ages. Look at this particular type of fire happened in Quebec building in Canada. the fire originated from the upper floor has spread in higher levels and also circumferentially and also spread in the below floors, and as a result the whole building was devastated completely by fire. So, fire in structures have a very undesirable effect apart from degrading the strength of the material. The structure loses its functional value. It also imposes safety for the buildings located adjacent to the structure, as well as it creates economic loss and environmental impact on the location where such accidents occur. Though we have learnt the classification of fire based on the fuel, etc., just to recollect what we have learnt, it is better that we get updated ourselves in that before we enter into analysis for fire. There are different types of fire as we see here, class A, B, C, D and K. A of course is fire involving organic solids like paper, wood, etc. B involves flammable liquids, C involves flammable gases, D involves burning of metals, and K, class K fire involves grease or oil, which is especially coming from cooking. Apart from this, electrical fires occurring from short circuits or electrical equipment malfunctioning can also be classified as type of fire. So, now let us ask a question: what are the possible structures which are exposed to fire loads? Generally, residential units or dwelling units are less prone to fire accidents compared to the following. 1. Heavy industrial structures where mechanical and chemical processes happen. Process industries such as LNG bottling plants, CNG as well as oil and gas processing plants, nuclear reactors which work at very high temperature, maritime structures which has got oil and gas production platforms as a subset of maritime structures, and of course chemical processing plants such as paint, cement and so on. So, these are the class of structures which are normally under high risk of fire loads. If you look at any specific structure under fire, what are the basic requirements which an engineer should undertake? Let us look at the devastating shape of the structural system when a fire attacks or engulfs a structural system. Structures therefore should be designed to withstand fire for a specific time. You cannot make a building as fire proof completely. You can only make a building fire resistant for a specific period. So, structures are generally designed to withstand fire for a specific period. So, no fireproof buildings exist, only fire resistant buildings can be designed. Structures therefore are designed for fire rating only. Then the question comes, what are the factors that govern this design? One is accessibility to firefighting system. Second is the location of assembly point in the building. Third one is the evacuation facility available in the building in case of fire, and the escape routes, their layout and operational functionality of these routes, and of course most importantly maintenance of fire hydrants and fire water lines which supply water during firefighting processes. Categories of fire is also done using international codes such as D and B. It can be categorized as no risk, low risk, medium and high risk fire. No fire risk refers to buildings which has no energy resources at all which can catch fire. Low fire risk buildings are those which actually has inventory of non-flammable materials. Even they can also catch fire, friends. We already saw even a sawdust and husk can also cause fire, which we call as dust explosion. Medium risk fire are those buildings where electric and major testing equipments are located. For example, laboratories, experimental facilities of academic universities, workshops where fabrication happens, they are all susceptible to medium fire risk. High fire risk of applied to those buildings where flammable liquid and high power electric machinery are under operation. So, maritime structures fall under this category. Okay, fall under this category. So, if we talk about fire resistance, we gradually realize that fire resistance amounts to computing or making a structure as fire rating. A fire resistance rating is that duration for which a passive fire protection system can withstand fire resistant test. Therefore, if a building is fire rated for 30 minutes, it means the building should remain structurally integral, may not be functionally integral completely, at least partially, but the structure should not collapse within that specific time. If the fire rating is slated as X duration, then the passive fire protection systems deployed in the structural system should withstand standard fire resistance test for that duration. So, this is generally quantified as a measure of time, usually in minutes or somewhere in hours. For example, if I say 1 hour fire rating, it consists of various building materials that can risk the exposure of fire, that is a standard fire, for 1 hour. So, 3 different criteria for fire resistance are load bearing criteria, integrity and insulation criteria. Let us see what are the design considerations for steel structures. We have already learnt in the previous lectures that when steel is exposed to high temperature, there is reduction in modulus of elasticity. So, the curve shows the typical reduction of modulus of elasticity with increase in temperature in classical structural steel used for construction. So, it degrades significantly, and the degrade starts at about 100 degrees Celsius onwards. Till 100 degrees Celsius, the strength or Young's modulus of steel remains as no reduction factor, after which it significantly reduces till about 500, then significant reduction till about 700, then actually at this point the strength or the Young's modulus becomes negligible. Okay. So, steel cannot retain its strength beyond, let us say, 600, unless otherwise it is made to resist fire or that temperature by some special alloying elements. So, the observation says that the modulus of elasticity decreases with increase in temperature beyond 100 degrees. It implies that there is a reduction in stiffness of the member, which leads to large deformation. You know, for example, the stiffness of the beam element is proportional to, let us say, EI by L, we call bending stiffness. The axial stiffness again is AE by L. So, in both these cases you would notice that stiffness is proportional to the modulus of elasticity. When the modulus of elasticity is decreasing, as you see here, therefore, the stiffness also degrades or gets reduced, okay, and that will induce large deformation, because we know that K delta is a force. So, the displacement will be very large for decrease in stiffness under a given force. Okay. So, it sees lot of or large deformations under the same load. Then what is the design consideration we must take into account? This incorporates that a reduced stiffness with increased deflection becomes a necessary input in the analysis. So, when we do a dynamic analysis, obviously the dynamic analysis of structures exposed to high temperature should account for large deflections with reduced stiffness in the analysis. So, therefore, reduction in modulus of elasticity accounts for reduction in stiffness in the design. Similarly, if you look at the yield strength factor, reduction factor for steel at high temperature, yield strength also reduces at high temperature. For example, till about 400, there is no reduction in yield strength, but it significantly drops to practically 0 at about 800. Okay. So, yield strength, which is one of the important strength design parameter in steel structures, also reduces with increase in temperature. So, yield strength starts decreasing significantly at after 400 at 2% strain rate. It implies that the structural components may fail to carry the design load at elevated temperatures beyond 400. The design consideration warns that I must use temperature dependent yield strength value in my analysis. Okay? In fact, the temperature dependent yield strength should become an input in my analysis. Okay, instead of using a constant sigma y, I must use sigma y as a function of temperature and time. Okay, that is the implication here. So, one must say the yield strength or Fy should now become function of temperature and time, so that this becomes an important input for my analysis. Other design considerations for steel at elevated temperature comes with ductility and thermal expansion. At high temperature, the ductility increases with temperature, allowing for large deformations before failure. So, the steel or the material or the cross section starts practically flowing, which is imposing large ductility. In fact, ductility ratio is what we see here. Let us take a typical stress strain curve of steel. A typical stress strain curve of structural steel looks like this. So, the salient points indicate that this becomes my yield stress and the corresponding strain, let us say, is my yield strain. This becomes my ultimate stress and the corresponding strain is my ultimate strain. So, now I can say the ductility ratio is given by ratio of strain at ultimate by ratio of strain at yield. Usually for structural steel, this value is about 6. Okay. And on the other hand, for our additional information, we can also say the ratio of ultimate stress by yield stress is given as strength ratio. Usually for a structural steel, this is about 1 point odd, okay, approximately 1.7. So, one can see here that the ductility ratio is usually large compared to strength ratio. Okay. So, we believe we invest on the ductility component of the steel property more compared to its strength, right. So, we say this is what is required for structures if you want to perform in nonlinear zone or post elastic deformation zones. So, what we try to say here is when there is increase in temperature, there is increase in ductility. The increase in ductility will make steel to flow at the constant load. So, without any increase in load, strain will be increasing. Okay. So, that will impose large deformation on the system before failure. The implication in the design is when the deformation capacity improves, the structural integrity and safety margin reduces. That is the difficulty here. We already said that in the last lecture. Let us say if I design a system using any design methodology. So, this is my design level, what we call as demand. Let us say the target or the capacity of the structure is here, which essentially comes from two. One is from the geometry, other is from the material. We discussed about form dominant design in other courses as well. So, geometry also gives you lot of redundancy, indeterminacy, strength, which is added to its capacity. In addition, of course, material also helps you to get the more strength. So, if this is my demand and the capacity, then we can say that this remains as my safety margin in the design. Let us look into the design aspect. If I say this is my demand which is arising from the loads, and I fix this as my capacity, which essentially comes from the geometry and material. The capacity from the geometry is what we refer to as form dominant design. It also comes from the indeterminacy offered by the supports and arrangement of members. So, all these put together are dominant by the geometric form. Therefore, we can say it is form dominant component of the capacity. It also comes from the material without any doubt. So, now let us say this is where my demand stops and this is the capacity. So, I could understand as a designer that this becomes my safety margin. Okay, this becomes my safety margin in my design. Now, when I subject this member to thermal stresses because of high temperature, then the member receives additional stresses and therefore, the demand increases. Okay. This becomes additional because of the increase in stresses by higher temperature. Furthermore, as we saw in the previous slide, the strength or the capacity also gets reduced at high temperature, because there is reduction factor, for yield strength, there is reduction factor for modulus of elasticity. So, they all get reduced at high temperature. So, if they become function of time and temperature, then at high temperature beyond 400, 600 etc., there is a significant reduction in both these quantities, which are actually depending on or contributing to the capacity. So, this reduction in capacity. Therefore, friends, it is very clear that the margin of safety when we do fire resistant design is much compromised compared to conventional design. Okay. So, there may be a situation where they will also become naturally or close to practically 0. I mean, there is no safety margin available and the capacity just touches the demand, and that is a place where we talk about fire rating etc. So, therefore, friends, when we talk about increase in ductility which imposes large deformation, then the design consideration should be very carefully done, because the connections and the joints now have experienced large deformation, and that should be checked so that they do not have any deformation leading to failure of connections. So, there is a reduction or compromise in safety margin. At the same time, the connections or the joints should be also checked for no failure case. Similarly, friends, when we talk about thermal expansion occurs in steel when there is a rise in temperature, and this will lead to elongation of members, because thermal expansion means the member elongates, the material permits elongation. This implies that they induced thermal stresses coming or arising from thermal strains in constrained systems. If the system is free to expand, no problem. If you constrain the system from boundary conditions like supports etc., then the system has constraint imposed on it that will lead to misalignment in the structural member. So, that is another implication. In the design, we account for this thermal expansion coefficients and provide thermal expansion joints in the design. Okay, you must have seen generally when the building is more than about 60-meter long, then we provide expansion joints. These are all because of the free deformation permitted to the structure in case of lateral loading. In addition to this, when the structure is subjected to or designed for fire resistance, you must also allow expansion due to thermal effects. So, that is the implication of this particular property when you do steel resistance for fire resistant design. So, look at the thermal conductivity and specific heat. Thermal conductivity is shown in this figure here, and specific heat variation with temperature is shown in the figure here. Let us look at thermal conductivity. Thermal conductivity changes significantly with increase in temperature, okay, which affects heat transfer within the material, whereas specific heat influences the rate of change of temperature rise in the steel members. Put together, they have implications on thermal or temperature distribution and rate of heating in steel member. So, therefore, friends, use fire insulation materials or coatings to control temperature rise and ensure uniform heat distribution. Okay. They should not cause any differential elongation or deformation caused because of thermal variation. So, one should use insulated materials. Okay. Now, we look at plasticity at elevated temperature. Steel becomes more plastic because lot of deformation happens at high temperature, reducing its proportional limit. It implies that the structures may exhibit permanent deformation, that is the word plastic. We already know plasticity is a property which exhibits or experiences permanent deformation before failure. So, the design consideration is these perform permanent inelastic analysis should be carried out for critical members to evaluate these plastic deformation limits. Specific weight of steel, or in general, the weight of steel remains mostly constant, but should be factored when designing against thermal effects because it changes. The design consideration is that ensure that temperature induced distortion or deformation do not lead to instability due to self weight. Okay. Fire resistant design has certain key properties to be defined. Number 1, define the reduced modulus of elasticity and yield strength as values of function of temperature. We already saw the curve, we know how to implement them. Temperature dependent thermal conductivity, specific heat and thermal expansion should be included in the analysis. Fire design standards follow different applications. For example, Eurocode 3 part 1-2 design of steel structures for fire resistance helps us to do fire resistant design. IS 800 structural steel design has got specific class of fire specific provisions in the design. One should also, apart from designing for safety in fire, should check for structural stability under fire loads. The major challenge here is at elevated temperature, because of large deformations imposed on material and the member, one may experience instability due to thermal buckling and lateral torsional buckling. Therefore, performing a stability analysis under elevated temperature conditions, considering reduced strength and stiffness becomes very important if you want to ensure that the building or the structure does not fail by thermal buckling and lateral torsional buckling. Fire protection systems are inherently part of such complicated structures like industrial structures, maritime structures, etc. There are many types of fire protection systems: active, passive. They should be design integrated. Active systems refer to sprinklers and water sprays. Passive system refers to fireproof coatings, insulation materials. One must include the passive and active fire protection systems in the design to ensure steel that maintains the integrity during fire exposure. So, one uses advanced finite element modeling in case of fire resistance to simulate thermal stresses, plastic deformation and failure modes at high temperatures. Nevertheless, friends, it is very important to incorporate temperature dependent material properties. Okay, as we just then saw in the previous slides, your analysis should include temperature dependent material properties in the simulations, not only temperature rise, but also time variance, because the temperature and time are interconnected in the strength degradation. Okay. So, this should include the temperature dependent material property and also the time dependence of temperature. Now, let us look at the question where how to perform fire resistant design. Let us take extracts of the equations from the code directly and see what codes advise as far as fire resistant design is concerned. Let us talk about the load resistance as R. The load resistance decreases with increase in temperature because the capacity of the system gets degraded. The material strength gets degraded at high temperature, we already saw that. Therefore, the resisting capacity decreases with increase in temperature. Okay. Therefore, the capacity under fire should be higher than the demand under fire. I mean, that is a general philosophy of design. Whether it is with or without fire, capacity should be always, or the resistance should be always exceeding the demand. The time at which this equality occurs is the fire rate. That is very important understanding of fire rate. What we say, when the resistance under fire is exactly equal to the demand under fire, it happens at a specific time. Okay? That time is what we call as fire rating of that structure. Usually, fire rating is expressed in minutes or in hours. Now, let us compare this design of fire resistance with conventional design. When we design a system for normal temperature, design under fire scenario typically demands the following. 1. There is a lower application of amplitude of loads. The load application becomes lesser in amplitude. There is a possibility of additional internal forces and displacements caused because of temperature rise, that can be due to thermal expansion. There is reduction of material strength. There is reduction in cross sectional area. If I talk about, you may say, when the steel is heated, steel gets expanded, diameter becomes larger, but the cover concrete all around the surface gets completely spalled off. We saw photographs and figures in the last lecture. So, therefore, there is reduction in effective cross section area because of spalling of concrete, and there is a possibility of failure mechanisms becoming different. For instance, one can also experience a local plastic hinge formation. So, those who have understood plastic design of structures, you will notice that hinges will form only when the structure is indeterminate, whereas plastic hinges likely may form locally even in determinate systems when the system is subjected to high temperature. Okay. So, there can be a change of mode of failure from elastic to plastic when you subject the structure to high temperature. Therefore, friends, in nutshell, compared to normal temperature design or ambient temperature design, fire resistant design has got the following inputs: reduced load, possibility of additional internal forces and displacements caused by thermal expansion, reduction in material strength, reduction in cross section area as a whole in concrete because of spalling of concrete, and there is a high possibility that the failure mechanism and mode of failure gets shifted from a conventional elastic analysis to plastic analysis, because there can be a formation of local plastic hinges at intersections where resistance deficiently falls below the demand. Okay, there is a possibility. So, therefore, friends, fire resistance amounts to estimating fire rating of a given structure. A fire resistance rating is referred to as the duration for which the passive fire protection system can withstand standard fire resistance. This is quantified in terms of minutes or hours. So, three different criteria are applicable: load bearing criteria, integrity criteria, and insulation criteria. So, load bearing criteria is referred as R in the narration, integrity as E, and insulation as I. So, we can look for either R category or RE category or REI category in design. Codes of practice for fire are referred to by different international provisions. Handbooks are available to help us to design systems for fire resistance. These handbooks give empirical equations which are based on experimental investigations. They also advocate smoke control and management of release of hot gases. And furthermore, friends, as you saw in the previous lectures, for doing estimate of fire loads, you need lot of engineering data. Okay? The mass concentrated on the space as well as the caloric value of this, and you may also require time, temperature, behavior of these materials. So, you need lot of engineering data to do fire resistant analysis or to compute fire loads on structures. Different standards are available for general rules of buildings, fire design for different structures, steel, concrete, composites, etc., fire and life safety, testing of materials under fire, methods of fire detection and fire protection equipments. There are different standards available for different segments of these verticals. So, what are different codes of practice internationally available to do fire resistant design? ISO 834-10-2014 fire resistant tests, which are useful for elements of building construction. Eurocode 1992 Part 1 to 2004, design of concrete structures. 1993 1 to 2005, design of steel structures, general rules. IS 3809, Indian Standard Code of Practice for fire resistant test for structures. National Building Code of India, NBC Part 4, fire and life safety. ASTM E11920, standard test methods for fire test for building construction and materials. DNVGL, operational standards or offshore standards, D301, offshore standards for fire protection. British standards 9999 2017, fire safety in design, management and use of buildings, code of practice. These are various codes of practice in national, international scenario which are currently available to us to understand fire resistant design. We will illustrate examples in the coming lectures using these codes and make you learn line by line different elements of examples for fire resistance. To have a simple note how to start with the design consideration, let us take a tension member. A tension member design is governed by this equation available on the screen, where Fy is the normal temperature yield strength. Remember, no factor reduction, normal temperature yield strength. And A fire is the area of cross section for which the fire resistant is undertaken. So, A fire is actually equal to cold sections because A fire allows consideration of scenarios where cross section area may reduce during the fire event. If N cold is actually equal to Fy into A cold, one may view the capacity of fire as N fire KYT into N cold. Okay, that is what we said. If N cold is Fy A fire or A cold, therefore, the reduction factor accounts for the reduction in strength and also the variation in the area of cross section. It is to be noted that there will be situations where material stress other than yield strength will be required. Example could be bolted connections, because the bolts what we use can be of a different category of steel. Therefore, we may require additional data for those materials which are different from the yield strength. The methodology, however, will not change and the corresponding strength reduction factor will also be similar. Look at design for flexure beams with lateral torsional buckling not critical. The moment carrying capacity is given by this equation. If you have lateral torsional buckling critical, then the moment carrying capacity is given by this equation. If you want to compute the critical buckling stress at elevated temperature, one can use equation number 3 to compute this. So, for using these equations, one may require the non-dimensionless slenderness ratio to check the moment carrying capacity before it buckles. So, it is given by this equation available on the screen. Therefore, the bending stress reduction factor for lateral torsional buckling at elevated temperature is given by this equation, where the phi LT is given by this equation. Therefore, friends, in nutshell, the moment carrying capacity at higher temperature is given by this equation as you see on the screen. In the successive lectures, we will show examples and use these equations and illustrate how to use them to compute the moment capacity as well as the fire rating. Let us wind up this lecture now by showing couple of slides. So, if I say I want to perform a numerical analysis, what are the steps involved in fire resistant design or analysis of structures under fire? So, I must compute a preliminary analysis, which is a conventional analysis where the structure is subjected to loads without any fire load. That is a step number 1. In step number 1, when we do this, we will be able to identify the critical points where the stresses are maximum, okay, from this analysis. Move to step number 2, we want to implement fire dynamics. That is, you can identify the critical locations where ignition sources are present in the given system, the likelihood of fire accident happen in the system. The third could be use this data along with this and do analysis under fire, estimate the fire load, impose it on the structure at every time step. So, one can see these red points where the possibilities of fire loads are induced, and one can also find out the temperature variation with temperature and how the temperature rise happens in a contained space using a software. Okay. So, we will explain this in the forthcoming lecture, a full numerical simulation of a structural system under fire loads using pyrosim. So, a typical analysis can also help you to find out HRR versus time. So, it will give me the heat release rate with respect to time as the system or the compartment is set to fire. One can also find out the temperature difference in the altitude of fire as you see. So, when you look at this figure, a compartment, whereas this is the part where the fire is set source, and look at this curve, at every interval of 0.3 meter vertically, the temperature contour has been plotted here with respect to time. So, one can see at this point, the temperature is maximum. Okay, this corresponds to this particular point, whereas this corresponds to this particular point. So, the temperature keeps on rising as you go towards the roof. Therefore, the hot gases gets accumulated here and they should be taken out or trapped out to make the system smoke proof and improve the fire in system under fire failure. So, therefore, friends, fire simulation includes preliminary analysis and fire dynamics. Structural response includes thermal analysis and coupled thermal structural analysis. So, there are two divisions in fire resistance. One is the fire simulation, other is the structural response for fire. One can also nevertheless implement updated properties of material, because material properties become temperature dependent. I must use temperature dependent data only. So, the thermal analysis includes density, conductivity, specific heat with respect to temperature. The coupled thermal displacement analysis include density, elastic modulus, Poisson's ratio, expansion coefficient and yield strength and plastic strain in the analysis. So, one can also illustrate this example very quickly on the screen, that the transfer of output from the fire dynamic simulator is implemented in thermal boundary condition, and one can generate the output database compatible with coupled analysis. One can see how the temperature increase with time causes thermal stresses on a given beam, what we say as thermal analysis results. So, if you do a coupled thermal displacement analysis, apply the external loads at that point and try to find out the heat transfer output from the structural system. Let us say this is the beam which has been subjected to thermal loading from here, and at that point apply the loading. So, what we say is we apply loads at two stages. Till stage 1 thermal loads are not applied except the structure is heated and reaches temperature. At this stage you apply the heat transfer load additionally. Okay. So, at this point the structure has already reached a stage where thermal gradients are set in the structural member, then you apply the load and do analysis. Okay. That is how we do application of load and temperature steps in abacus for doing analysis. So, friends, let us come to the summary of this lecture. In this lecture, we learnt about the classification of fire, we reviewed them again, we already learned them, we reviewed them again. We also knew and understood how fire analysis steps can be chalked out, what are the steps. We learned that fire causes reduction in Young's modulus, reduction in yield strength, variations in specific heat, it improves or increases ductility, it imposes additional thermal stresses, and that is a worry because this compromises the safety margin in design. We have also saw some of the design codes, equations for tensile or the beam member under fire. We will also do one more example of numerical simulation in the coming lecture to make you understand how this analysis of structural system under fire can be carried out using a software. Thank you very much. Stay with us connected. Bye.